So Sandeep sir, shall we start, sir? It is 9.
Yes, sir. I think you can start.
Okay, sir. Is it visible, sir? Sandeep sir?
Yes, sir. It is visible.
Yes, sir. So good morning, students. So today we'll start with the 5th chapter, Electromagnetism and Magnetic Properties of Material, chapter 5. It's a very simple chapter topic. It consists of 3 parts. The entire chapter is divided into 3 parts. The first part goes with electrostatics. Second part goes with basics of dielectrics. And third goes with basics of magnetism. Now, electrostatics. Electrostatics is not something new to you. In your intermediate second year, you have already seen this. Basically, electrostatics deals with study of static or stationary electric charges. It deals with stationary or static electric charges. Right? There are 2 laws in electrostatics. First law, as we all know, like charges repel each other and unlike charges attract each other. Second law, the more famous Coulomb's law. According to this law, two charges attract each other or repel each other with a force which is directly proportional to the product of their charges and inversely proportional to the square of the distance between them. The more famous Coulomb's law. This is the second law. First law, like charges repel each other, unlike charges attract each other. Second law, Coulomb's law. Next, equation electric current and equation continuity equation. Generally, this particular law is never asked in JNT examination, but still it only defines the rate of flow of charges. The rate of flow of charges is nothing but current. Current is given by Q by T, charge by time. And the point form of this particular continuity equation is given by Ohm's law, given by J equal to sigma E, where J is current density, sigma is conductivity, and E is electric field. Fine. Next, Gauss law. According to Gauss law of electrostatics, the total electric flux enclosed in a closed surface is equal to the net charge enclosed by the surface. Please remember the equations and the statement. The total electric flux through a closed surface is equal to the net charge enclosed by the surface. See the equations, the integral forms, integral E dot dA equal to Q enclosed by epsilon naught. Epsilon naught is the permittivity of free space. Next, you have Ampere's law. According to Ampere's law, the line integral of magnetic field around a closed curve is equal to the net current enclosed within the loop. The line integral of magnetic field over any closed path is equal to the total amount of current within the loop. All these laws you should have seen in your +2 classes only, but most of you might have forgotten it because of you have come with a different into a different stream and with different subjects. Okay, anyhow, the statement is integral around a closed curve b dot dl equal to mu naught I. It is the integral form. Please see the differential form given at the bottom. Del cross H equal to J. Del cross H magnetic field intensity equal to J. J stands for current density. Faraday's law. According to Faraday's law, the magnetic flux linked with current changes. Whenever a magnetic flux linked with current changes, then an EMF is generated. It has two laws. The first law is whenever the magnetic flux linked with the current changes, then an EMF is induced. Then second law, the induced EMF has a magnitude which is equal to the time rate of change of the flux. Fine. Then the equation E equal to minus d phi by dt. Phi is the magnetic flux and E is the EMF induced. In general, if there are n loops of a coil, then the total EMF induced will be equal to minus n into d phi by dt. Minus sign indicates the opposite direction for the current. The concerned Maxwell-Faraday equations are given here. See the integral form. Minus integral E dot ds equal to minus d by dt integral b dot ds. Wherever we are using ds means it is surface only. Next, Lenz's law. According to Lenz's law, the direction of induced EMF will be such that if it were to cause a flow of current in a conductor and external, then current would generate a field that would oppose the change, the very change that created it. We know this law. See the statement EMF equal to minus n into d phi by dt or del phi by del t. It is a consequence of Faraday's law itself, Lenz's law. Next, please see the four Maxwell's equations. Maxwell's equations in integral form and differential form. In the first part of electrostatics for the syllabus, you only have the statement of Gauss law, Faraday's law, Ampere's law, and Lenz's law. I repeat, in the first part of electrostatics, you have the definitions of Gauss law, Ampere's law, Faraday's law, Lenz's law, and the four Maxwell's equations. You do not have any derivation with respect to syllabus. Just in case if you are asked, usually Maxwell's equations are asked either as one equation will be asked in the internal objective examination, or if at all given in the external examination, 2 years they have asked for 3 marks. Write the four Maxwell's equations. That's all. They did not go for any derivation. In fact, derivation is not there for you in the syllabus. Right? We'll continue with the major part of the next chapter, dielectrics. Dielectrics and magnetic properties of materials. Now, to begin with dielectrics, the first part of dielectrics is dipoles. Dipole. Defining it, two equal and opposite charges separated by a distance d will form an electric dipole. Two equal and opposite charges separated by a distance d will form a dipole. So you have plus and minus q charges separated by an r, distance r from center to center. This combination is an electric dipole. Now, the product of one of the charges and the distance between them is what we call it as dipole moment. The product of one of the charges and the distance between them is called electric dipole moment, mu. So the units of electric dipole moment will be unit of charge is coulomb, unit of distance is meters. So units will be coulomb meter. Electrostatic units are dBi, dipole moment. Next. So basically, what are dielectrics? Dielectrics are nothing but they are materials in which the electric field can be contained for a longer duration of time, but at the same time, the material offers a very high resistance to the passage of electric current. Just a second. So basically, dielectrics are materials in which the electric field can be contained for a longer duration of time, but at the same time, the material offers a high resistance to the passage of electric current. Now, what are those materials you call which offer high resistance to the passage of electric current? We call them as insulators. So basically, dielectrics are nothing but insulators. Then why don't we call them as insulators? The reason being, Insulators do not contain electric field, whereas dielectrics do contain electric field. Dielectrics are classified into two categories, polar dielectrics and non-polar dielectrics. To put it in a simpler way, polar dielectrics are those which have some finite value of dipole moment. That means dipoles are present in the material. Non-polar dielectrics are those which do not have any dipoles, means the resultant dipole moment is zero. If dipole moment is finite, then you call it as a polar dipole, polar dielectrics, and if dipole moment is zero, you call it as a non-polar dielectric. Fine. Next, you can see here, I am showing you a polar dielectric. The diagram indicates a polar dielectric. Next, dielectric constant. All of us have come across this particular value. In sciences or in intermediate, we also use the word permittivity for it. I will see what is permittivity. No. Before going into dielectric constant, let us define another terminology, permittivity. Permittivity, we have heard this word. Permittivity basically is the ability to store electrical energy, or in general, to be more precise, permittivity indicates the ability of a medium to permeate the electric lines. If electric field, electric lines of force or electric field can move through it, can permeate through it, that property which is indicated is called as permittivity. So basically, permittivity is the ability of electric lines of force to move in a medium or to permeate in a medium. It is given by the symbolic representation epsilon. Now, permittivity for free space, epsilon naught, the ability of electric lines of force to move in free space is a constant given by the value epsilon naught equal to 8.85 10 power minus 12 farad per meter. Similarly, every medium has got some permittivity, and that relative permittivity, that is called as relative permittivity, is given by epsilon r, which is the ratio of permittivity of the medium to the permittivity of free space. This relative permittivity itself, we call it as dielectric constant. Next, there are three electric vectors you need to remember. Electric flux density given by D. It is the ratio of charge by area, the total amount of charge enclosed in a specific area, Q by A, is called electric flux density. So units will be coulomb per meter square. D is electric flux density, Q is charge divided by area. Next, electric field intensity. Electric field intensity is given by V by D. V is the voltage across 2 points, between 2 points, divided by the distance between the points, V by Q, or the units are volts per meter. It is also defined as the force experienced by a unit charge placed at a point in the field. In that case, the units will be Newton per Coulomb. Right? Next, the third quantity is polarization vector P. Polarization vector P is the total amount of dipole moment present or expressed in a material. The total amount of dipole moment is charge into distance. The total amount of permanent or induced means giving it externally, amount of dipole moment present in a material. A simple relationship exists between the three vectors, electric flux density, field intensity, and polarization vector, given by epsilon naught E plus P. Please remember this. Epsilon naught E plus P. Almost every year they are asking it in university internal examination, second internals, as an objective question. D equal to epsilon naught E plus P. Now, what exactly next important topic is polarization. Electric polarization, it refers to the creation of dipoles. If at all we have a non-polar dielectric and we want to convert it into polar dielectric, that means non-polar dielectric has zero dipoles. There are no dipoles. So you have to create dipoles. How do we create? By applying electric field. When you apply electric field, the centers of positive charges and negative charges separate from each other. then a dipole is created, and that dipole will have dipole moment. This process of converting a non-polar dielectric to polar dielectric, or the process of inducing dipole moment in a non-polar dielectric, is called as polarization. And this can be done only by applying electric field. There are three types of polarizations: electronic polarization, ionic polarization, and orientational polarization. Electronic polarization is generally seen in elements and some kind of metallic materials. If you separate the positive and negative charges, then a dipole is created in the material. It is also done only by the application of electric field. In the first circle, you can see on the left-hand side below the definition, it consists of an atom. Basically, the central blue color with a plus symbol is the nucleus. So the external yellow color or black color circle is the negatively charged electron cloud. Now, try to visualize it. This negatively charged electron cloud and the central nucleus have a common center. So it is a non-polar dielectric. See the second diagram. Now, if I apply the electric field, the negatively charged electron cloud will be repelled opposite to the field, and the positively charged nucleus will get attracted towards the electric field. So now the centers are separated. Now it means a dipole is created. So by applying electric field, you can separate the centers of positive and negative charges. The total amount of electronic polarization present in any material is given by 4 pi epsilon naught r cube, where r is the distance between center of positive and negative charges. Pi is a constant, epsilon naught is permittivity of free space. Next kind of polarization is ionic polarization, usually seen in ionic materials. For example, sodium chloride. It is an ionic crystal which consists of cations and anions. So if you apply electric field and separate the centers of cations and anions from each other, then that kind of polarization is called as ionic polarization. The ionic polarization is given by a value of E square by omega square into 1 by m1 plus 1 by m2, where E is the electronic charge, omega is the angular frequency of the ion. Both cations and anions have the same angular frequency of vibration. M1 is the mass of cation and M2 is the mass of anion. So M1 and M2, the masses of anions and cations are different. So this is the formula for ionic polarization. Next, please see this diagram. Initially, the cation and anion are combined together. Now, if you apply electric field, see the third diagram, the centers of cations and anions are separated. But in the third diagram, you can see the negative ion has a bigger circle surrounded by it and the positive ion has a smaller circle surrounded by it. The reason being, cations in general are larger than the anions in size. The third kind of polarization is called as orientational polarization, which is usually seen in some kind of organic molecules like benzene or some kind of neutral molecules also. For example, water also has the property to exhibit orientational polarization. Mean to separate the charges, positive and negative charges in a molecule like benzene or in water, then the electric field applied and the process of separation is called orientational polarization. And this value is given by mu square by 3 kT. Mu is not a dipole moment here, but mu is magnetic moment of the material. I think there's a question. Let us take the question. Oh, no question. Fine. Where mu is the magnetic moment, it is not dipole moment. There's a question from roll number 503. Do we have derivation of polarization formulas? If you have only derivation of ionic polarization. Orientational polarization derivation is not there in the syllabus. Electronic polarization is very rarely asked. From the last 3 years, they have never asked. But orientational polarization, you can go for it. It is very simple, 3-step derivation only. Okay, fine. We'll continue with polarization. So mu square by 3 kT, where mu is magnetic moment. Please do not get confused. Here mu is not dipole moment because mu is the is the symbol we have attached to dipole moment at the beginning of the chapter, where K is Boltzmann constant and T is the temperature. Fine. These are the diagrams associated with orientational polarization. In fact, orientation polarization, we have only basic definition sentence and the formula. Langevin-Debye equation. Do not get confused. 2 years back in a supplementary examination, they asked, it was for 2 marks. The question was, write the Langevin-Debye equation. Now, many people get confused as to whether it is there in the syllabus. Nothing. Add all the 3 individual polarizations. Add all the 3 individual polarizations, electronic, ionic, and orientational. See the third equation, not the first and second, third equation. Mu 4 pi epsilon naught r cube, E square by omega square 1 by m plus 1 by m, mu square by 3 kt. This net equation is called Langevin-Debye equation. If you add all the individual polarizations, the resultant equation is called Langevin-Debye equation. It is generally asked for 2 marks in the external examination. Just generally to test whether the student has gone to the textbook or not. That's all. Next, internal fields. What is an internal field? When you apply electric field to a dielectric, some amount of electric field is stored inside the dielectric material. That stored electric field inside the dielectric is called as the internal field of the dielectric, which is given by E plus P by 3 epsilon naught, where EI is the internal field, E is the externally applied electric field, P is the polarization of the material or the polarization vector, and epsilon naught is the permittivity of free space. Next, this is the electric internal field equation. You do not need to go through this internal field derivation. Clausius-Mathothys equation. According to Clausius-Mathothys equation, it expresses a relationship between dielectric constant and the polarizability of the material. See here, the dielectric constant here is given by K or epsilon r. Epsilon r minus 1 by epsilon r plus 2 equal to n alpha by 3 epsilon naught. Epsilon r is the relative permittivity or dielectric constant. My K minus 1 by K plus 2. Instead of K, I have written it as epsilon r here. Epsilon r minus 1 by epsilon r plus 2 equal to 1 by 3 epsilon naught into n. N is the total number of atoms to be polarized or total number of atoms that are to be created as dipoles. Alpha is the polarizability of the material by 3 epsilon naught. Epsilon naught is the permittivity of free space. Instead of polarization vector P, I have used here as alpha. That's all. Instead of P, I have used it as alpha here. Now, ferroelectrics. Next topic is ferroelectrics. What are ferroelectric materials? Basically, ferroelectric materials are those which contain polarization even in the absence of an external electric field. That means dipoles are already present in the material. In the beginning, we have discussed dielectrics are of 2 types, polar dielectrics and non-polar dielectrics. Those polar dielectrics are called as indirectly as ferroelectrics because they already have dipoles present, dipole moment present in them. We don't need to create any dipoles and dipole moment inside the material. Those kind of polar dielectrics, we call them as ferroelectric materials. So they exhibit electrical polarization, dipoles, dipole moment, even in the absence of an external electric field. Examples are barium titanate, Rochelle salt, potassium dihydrogen phosphate, ammonium dihydrogen phosphate. Now, please note, the polarization does not vanish when the external field is removed. If you apply electric field to a ferroelectric material, some amount of additional polarization is created. But if you remove the electric field, the polarization does not go away. It is like this. Take a bar magnet and try to rub it over a regular bar magnet. What happens? The magnet, if you remove the other external magnet, the original magnet will not lose its magnetism because it is already a bar magnet. Same is the case with ferroelectric. Take a ferroelectric material and apply electric field to it. Now, if you take away the electric field, the ferroelectric material will not lose its property of ferroelectricity. So that property is what we are calling it as polarization. Properties of ferroelectric materials. All ferroelectric materials exhibit spontaneous polarization, and as the temperature increases, this spontaneous polarization decreases up to a particular temperature. Please remember, the catchword is Curie temperature. The temperature at which a ferroelectric material gets reduced with polarization is called Curie temperature. And the dielectric constant varies according to the relationship C by T minus Tc, where C is Curie constant and T is the externally temperature and Tc is the Curie temperature, the temperature at which spontaneous polarization decreases in the material. All ferroelectrics exhibit the property of hysteresis, and all ferroelectrics exhibit the property of piezo and pyroelectricity. Now, the property of hysteresis is there for you with respect to magnetic materials, not with respect to ferroelectric materials. So I'm not discussing hysteresis of ferroelectric materials. It is there only with magnetic materials, and after 10 minutes I shall discuss that property also. Now, they exhibit the property of piezo and pyroelectricity. Applications. They are used for making capacitors, RAMs, radio RFID tags, and so on. These are the three applications of ferroelectric material. Next, piezoelectricity. Piezoelectricity is nothing but the creation of electric charges by applying mechanical force. Take two crystals, take one crystal, take a single crystal. Let us suppose it is cubical in shape. You apply mechanical force on the top and the bottom of the two faces. Then what will happen? Two perpendicular faces, you will observe electric charges created. If you apply mechanical forces on two faces of a crystal, then on two perpendicular faces of the same crystal, you have electric charges created. This process of creation of electric charges by application of mechanical force is called as piezoelectricity. Examples of piezoelectric crystals are barium titanate. Barium titanate is also a ferroelectric material. The applications are in ultrasonics and in crystal oscillators. Next, the third topic in the chapter is magnetism. Strictly speaking, we have magnetic properties of material. We do not have complete magnetism. We have only magnetic properties of materials. Now, as we have started with an electric dipole with dielectrics, we'll start here with a magnetic dipole. Two equal and opposite poles separated by a distance between them is called as magnetic dipole. Two equal and opposite poles separated by a distance forms a magnetic dipole. The product of the pole strength of one of the poles and the distance between them will give you magnetic dipole moment or magnetic moment. In general, any pole is measured in terms of pole strength. The units are ampere meter. And the distance between the poles is also called as the length of the magnet, which is given by 2L. So the product of the pole strength of one of the poles and the distance between the poles is what we call it as magnetic moment or magnetic dipole moment. M into 2L. Units are ampere meter square. Next. In some cases, magnetism can also be created by application of a current by flow of electric field. In such cases, what will be the magnetic definition of magnetic moment or magnetic dipole moment is, please see, if current is flowing in a circular loop, then magnetic field is generated. The product of the current flowing in the loop to the area of cross section is called as magnetic moment or magnetic dipole moment. In such cases, we'll take the product of current and area of the circular coil to define magnetic moment or magnetic dipole moment. In case of bar magnet, it is M into 2L. In case of magnetic field generated due to flow of current, it is I into A. I is the current flowing in the coil and A is the area of cross section of the coil. Next, as we had electric field density, electric flux density, electric field density, and polarization in dielectrics, we have magnetic flux density, magnetic field intensity, and magnetization in magnetism. So magnetic flux density is flux per unit area. Total magnetic lines of force or magnetic flux per unit area is called as magnetic flux density. It is also called as magnetic induction also. B equal to phi by A. Phi is the magnetic flux, A is the area. So units will be Webers per meter square. The other units of magnetic flux density are Webers per meter square is also called as Tesla. Webers per meter square is also called as Tesla. And the other CGS system of units are Gauss. 10 to the power of 4 Tesla will be equal to 1 Gauss. Gauss. Next, magnetic field intensity H. It is defined as the force experienced by a unit north pole placed at a point in the field to 1 by mu times. 1 by mu. Mu is the permeability here. Mu is the permeability. So 1 by mu times the force experienced by a unit north pole placed at a point in the field. Mu is the permeability. F is the force experienced by a north pole. M is the pole strength. M is the pole strength. The units of magnetic field intensity H are amperes per meter. And a relationship exists between B and H given by B equal to mu into H. Third quantity is magnetization. It is defined as the total magnetic moment per unit volume of the material. Magnetic moment per unit volume of the material. Magnetic moment is given by, M into 12, product of pole strength and length of the magnet divided by volume of the material, area into 12. So units are again amperes per meter here. Both magnetic field intensity and magnetization have the same units. Please remember that. A relationship exists between B, H, and I. Magnetic flux density, magnetic field intensity, and magnetization I, given by B equal to mu naught into H plus I. Permeability. As we have seen, permittivity as the ability of the medium to allow electric lines of force to pass through it. Permeability is the ability of the medium to allow magnetic lines of force to permeate through it or to flow through it. The ability of magnetic lines of force to move in a medium is called permeability. Similarly, you have permeability of free space given by the ability of free space to allow magnetic lines of force to pass through it is permeability of free space. It is a constant given by 4 pi into 10 power minus 7 Henry per meter. 4 pi into 10 power minus 7 Henry per meter. There's again relative permeability. Again, as we have relative permittivity, we have relative permeability given by permeability divided by permeability of free space called as relative permeability. Mu r equal to mu by mu naught. Now the relationship between B, I and H as given in the previous slide is same here. B equal to mu naught into H plus I. Next, susceptibility. The ratio of magnetization of the material to the magnetic field intensity, I by H. Both I and H have the same unit. So there are no units for susceptibility. So it is a dimensionless quantity. Susceptibility is the ratio of magnetization to magnetic field intensity. If it is a dimensionless quantity and is just ratio of magnetization and magnetic field intensity, then what is the importance of it? Now, the importance of susceptibility is that only based on susceptibility, you categorize magnetic materials. Only based on the value of susceptibility, you categorize magnetic materials into 3 categories. They are diamagnetic materials, paramagnetic materials, and ferromagnetic materials. If susceptibility is negative, please remember, in the question in the external examination, if he gives a negative value of susceptibility, means it is a diamagnetic material. Only diamagnetic materials, which are non-magnetic materials, which are never attracted to any magnetic field, is called diamagnetic material. All those materials have negative susceptibility. If the susceptibility is positive and less than 1, it means it is a paramagnetic material, means feebly attractive to magnetic field. If the susceptibility is positive and greater than 1, means strongly attracted to magnetic field, then you call it as a ferromagnetic material. Diamagnetic materials properties. Diamagnetic materials are those which do not contain any magnetic moment. There are no dipoles in them, no magnetic moment. Their susceptibility is negative and it is usually less than 1. It is independent of temperature. Even if you increase the external magnetic field also, the magnetic susceptibility will never increase. It is independent of temperature. When placed in a strong magnetic field, the magnetic lines of force are pulled out of the material. That means even if you place a diamagnetic material in a strong magnetic field will be greater only outside the material and not inside the material. Examples of diamagnetic material are air, water, gold, etc. Next, paramagnetic materials. Paramagnetic materials possess weak magnetic moment and weak magnetism inside the material. The susceptibility is usually positive and less than 1, and it is inversely proportional to the temperature, given by the relation C by T, where C is Curie constant and T is temperature. When you place a paramagnetic material in a strong magnetic field, then magnetic lines of force are pulled inside the material. That means magnetic field is greater inside the material than outside the material. It has the ability to exhibit magnetism, paramagnetic material. So it will pull the magnetic lines of force inside it, within itself. Example are oxygen and chromium. Now, next, ferromagnetic material. Ferromagnetic materials possess strong magnetic moment and they have strong magnetic field present inside them, even in the absence of an external field. If you apply it in external field, magnetic moment may increase in it, but it will never decrease in it. The susceptibility is positive and greater than 1. And with respect to temperature, it varies according to the relation C by T minus Tc, where C is Curie constant, T is temperature, and Tc is Curie temperature. When placed in a strong magnetic field, the lines of force are pulled strongly towards the center of the material. So magnetic field is greater inside the material than outside the material. Example, iron and cobalt. Next. Please remember this Bohr magneton. It is not there in the syllabus actually, but last year in the internal examination, last semester only, I should say, in the internal examination, in the second internal, they asked one question: the value of Bohr magneton is. That's all. So, Bohr magneton. See why ferromagnetic and paramagnetic materials exhibit magnetism is there is a quantity called Bohr magneton present in the material. If any material possesses some value of Bohr magneton, the material will be magnetic material. And Bohr magneton is given by the formula EH by 4 pi m, where mu b equal to H by 4 pi m, where mu b is Bohr magneton, E is the electronic charge of an electron, H is Planck's constant, 4 a number, pi a number, m again happens to be the mass of an electron. Fine. If you put all these constants and calculate, then you will get the value of Bohr magneton as 9.27 to 10 to the power of minus 24 ampere meter square. Please remember this formula. Value automatically you can calculate if at all even you do not know. Next. Domain theory of ferromagnetism. Why do ferromagnetic materials exhibit strong magnetic field? What is the reason for it? The reason is all ferromagnetic materials are divided into various regions. Please see, I am showing you a slide where the ferromagnetic material is divided into various regions. Each region, you can see all these cross lines zigzagly aligned. And in each region, you have magnetic dipoles in one direction. The magnetic dipoles are aligned in different directions in different domains. But so that is the reason why the material has some kind of magnetism present in it. It has got some spontaneous magnetization present in it because there are dipoles present in it. But the dipoles are aligned in different directions in different domains. Each region is called as a domain. And in each domain, there are dipoles present in it, and they are oriented in different directions. But when you apply an external magnetic field, what will happen is all the domains will come into one direction. Now, if you apply magnetic field, all the domains will be aligned only in the one direction. Now, the material starts exhibiting a permanent magnetic properties. This is the reason why permanent magnets are always manufactured only using ferromagnetic materials, because it is easy to align the dipoles in one direction. Now, when you apply magnetic field to a ferromagnetic material, what will happen is the domains grow in size, and all the dipoles in that domain will come in all the domains will align in one direction. So now if you remove the magnetic field also, now there is no difference all the domains will not go back into their original position where they were randomly oriented. They will remain in this field only. The conclusion of domain theory is that if we cut a magnet into two parts, then each part will behave like a magnet having south and north poles. This explains the reason for ferromagnetic properties. Second is, iron is magnetically soft, easy to magnetize and demagnetize. The reason being, you are bringing iron is generally used as permanent magnet. The reason being, easily there are dipoles present in it in different domains. If you magnetize it, all the dipoles will come into one direction. In a diamagnetic, that doesn't happen. In paramagnetic also, it is difficult to achieve it. But in ferromagnetic materials, it is very easy to achieve it. Steel is magnetically hard because impurities make it more difficult for the domains to align up. So in steel, you do not find this property of magnetic domains. So it is difficult to magnetize and demagnetize steel. Now the fourth property we know, by heating or hammering, domains are ruptured and the directions of dipoles in the domains are disoriented, and this causes to lose its magnetism. Now, please remember the most important property of ferromagnetic materials is hysteresis. We have seen hysteresis in ferroelectrics also, but we do not have it discussed it there. We'll discuss magnetic hysteresis. Now, what is hysteresis means? Hysteresis is a graphical way of plotting a graph between two parameters where one of the parameters will always lag behind the other. Hysteresis is a graphical plot and explanation between two parameters where one of the parameter will be always lagging or one of the parameter is always leading. If one is leading means other is lagging. If other is lagging means one is leading. Now, see the graph. The graph is plotted between two quantities, H and B, magnetic field intensity and magnetic flux density, or magnetic induction. H is B. H and B. Okay. Please see the graph. The graph starts from the point O. It starts from the point O. So initially the material is non-magnetized. So now if I increase the magnetic field, what will happen? The magnetization of the material will go up to the point A. I'm increasing magnetic field, but it will not, but according to hysteresis property or ferromagnetic property, it will not be a linear one. It will increase non-linearly. From O, it is going up to the point A. Beyond the point A, even if you increase the magnetic, see, take a bar magnet, you magnetize it. After it gets completely magnetized, even if you apply external magnetic field, there is no further increase in magnetization. It is a maximum saturation point. So that A is the saturation point. Now, if you remove the magnetic field, please remove the magnetic field now, then the curve does not go in the same way as it has increased, but rather it goes up to the point B. B. At B, please see the point B. At B, H value is 0. Magnetic field is 0. But is B value 0? No. Magnetic induction is not 0. That means for a ferromagnetic material, even if you remove the external magnetic field, magnetic moment is still, magnetization is still present in the material. This is called residual magnetism or remnant magnetization. Further you decrease it, then it comes to the point C. At point C, H is finite. Magnetic field is present in the material, but magnetization of the material is zero. Even if the material has magnetic field, but magnetization shows zero. This is a special case of ferromagnetic materials, and the point C is called as coercive field or coercive force. Further you go down to the point D, decrease the magnetic field, it comes to the point D, exactly opposite to the point A. A was the point where maximum saturation was achieved. Now D will be the point in the opposite direction where negative saturation of the material will be achieved. Means all the dipoles which were now oriented along A will now turn back to the point D. They will turn back to the point D. From D, again you increase the magnetic field in the opposite direction, it comes to the point E. The point E is similar to the point B. Field is zero, but magnetization is not zero. Residual magnetism or remnant magnetization is present. Again, further increase the field, it will come to the point F. F is the point where field is present, but magnetism is zero. Further you increase it, again it comes back to the original saturation point A. So you have started at point O, but it will never be possible. It is impossible to come back to the point O. For a ferromagnetic material, between B and H, increasing H and B or increasing B and H, if you plot a graph, one of them will always be leading and one of them will be always lagging. At point B, please see at the point B, B is leading but H is lagging. At point C, H is leading but B is lagging. Again at point E, B is leading, H is lagging. In this way, one of the quantity will be always leading and the other quantity will be always lagging. This is a special category case of ferromagnetic materials. They exhibit the property of hysteresis. Same graph here. The respective note is given here. I have given the complete notes of hysteresis along with the graph here. The curve ABCDEFA is called as the hysteresis loop curve. Now, based on hysteresis loop, magnetic materials are again classified into two categories. If the hysteresis loop area is small, then they are called soft magnetic materials. And if the hysteresis area loop is more, the loop area is more, then they are called as hard magnetic materials. Just to differentiate between types of magnetic materials. Applications of ferromagnetic materials. Many applications in making of permanent magnets, in magnetic data storages, to construct transformers and toroids, and in making super paramagnetic materials, recording tapes, audio and video applications. These are the few applications of ferromagnetic materials. So with this, we close the 5th chapter. If you have got any questions, please type in the chat box. If you have got any question, please type in the chat box. So I suppose there is one question. Sir, what are the important topics in Unit 5? Important topics in Unit 5 are classification of magnetic materials into para, dia, and ferromagnetic materials. And the most important question is, what is domain theory of ferromagnetism and what is hysteresis? These are two important topics in magnetic materials. Coming to dielectrics, the important topics are what is Clausius-Matthesius equation, what are ferroelectric materials, and types of polarization. Types of polarization: electronic, ionic, orientational polarization. What is Clausius-Matthesius equation, and what are ferroelectric materials? These are the important topics. And coming to electrostatics, you only have the basic definition of the four laws. What is Lenz's law, Faraday's law, Ampere's law, Gauss law, and their equations and Maxwell's equations. Roll number 5 and 8. Do we have problems to solve or derivations in the examination? See, actually, there is a derivation. There are derivations in the internal fields and electronic polarization. But I presume that this year they won't be asking it. The reason being, classes were not held regularly. So the questions are, I heard that, I expect that questions will be framed in such a way that too much of depth of the answering is not required by the student. That is what I presume. Do we have problems to solve? Yes, in magnetism, you will have problems to solve on simple problems. For example, calculate magnetic flux density, D equal to 5, B equal to 5 by A. Flux will be given to you, area will be given to you. You need to solve this problem. What is susceptibility in that way? Sir, once explain semiconductor lasers. Yes, I will. Okay. I'll start with semiconductor lasers. Okay. There is one more question. So please send all the important answers of 5 units with the notes. See, notes and PPTs and are already been uploaded yesterday itself, and notes are also given. Important answers you can find it in the notes itself. All the things we have given it there. See, semiconductor laser. Please respond whether you are able to see it or not, at least by typing in the chat box. Principle of semiconductor laser is nothing but you take a PN junction diode, and supply an electric field, apply an electric field. Is it visible now? Oh, sorry. You can't see it. I'll try to change the background. Wait. Try to change the background. The 50 unit PPT has already been shared yesterday. Roll number 515. Okay. See, there is some problem with this PPT. Roll number 1230, please switch off your video. See, there is some problem with this one. I'll just explain you. A semiconductor laser is a one in which for any laser to be generated, you know that we need three things. We need an energy source, active medium, and optical resonator. In a semiconductor laser, the energy source is an external electric field. We apply external voltage to it. Active medium is nothing but a semiconductor crystal itself. And optical cavity is nothing but we need to arrange two mirrors. We don't arrange the mirrors. We just polish the ends of the semiconductor. We just polish the ends of the semiconductor, and each end, one end will be completely polished, the other end is partially polished. So one will become fully silvered mirror, the other will become partially silvered mirror. Now, there are two types of semiconductor lasers. One is called homogeneous semiconductor laser, the other is called heterogeneous semiconductor laser. Now, the difference is in a homogeneous semiconductor laser, the PN junction, which is the active medium, is made with the same type of material. For example, P-type material is also made with gallium arsenide. N-type also is made with the gallium arsenide. So PN junction is the active medium. In a homogeneous semiconductor laser, both P and N are made with the same type of semiconductor material. For example, gallium arsenide. In case of heterogeneous semiconductor laser, P is made with gallium arsenide and N can be made with cadmium telluride. So P is different material, N is different material. This is the only difference between homogeneous and heterogeneous laser. Now, when you put a PN junction, connect a PN junction across with specific material composition, connected in a forward bias mode with external voltage, then the semiconducting material will emit photons of some particular wavelength of light, The emitted wavelength of light is the laser radiation. Now, you may ask, will every semiconductor material exhibit this property? No. The reason being, only specific composition of semiconductor materials are emitting laser wavelength and laser light. Those semiconductor materials are, for example, gallium arsenide you have, cadmium telluride you have, and so on. Every other kind of semiconductor material will not exhibit. Fine. This is the basic difference between a semiconductor laser, homojunction semiconductor laser, and heterojunction semiconductor laser. In a heterojunction semiconductor laser, you do not have it in the syllabus. It is only the difference between homojunction and heterojunction semiconductor laser. I'm sorry, I could not show you the PPTs. It is actually sent to me by my other colleague, but they are not. I am unable to change the background design of this PPTs. If there is any question, you let me know. I can answer it. Yes, 4th unit PPT, I have sent it. But along with that, on the KMIT online, I have uploaded 4th, 5th, and 3rd units also. Roll number 5 and 5. Roll number 5 and 8, we have received only 4th unit PPT. 5 and 8. I have already uploaded 3rd, 4th, and 5th. And Udayalakshmi madam will be uploading 1st and 2nd. Yesterday, she should have already done it. So, if there are any other questions, you let me know, because other class will be starting now. So, if you have, if you study this roll number 570, if you study these PPTs more or less, you will be able to attempt most part of the examination. You need to just expand the answers more or less. Samiha Gauss, semiconductor laser. See, I am unable to show the PPTs here because they are not my PPTs. It have been sent by someone else. We are available in the college regularly. If you can make it one day for a half an hour or so, then I will be able to clarify your doubt. Throughout this week and next week also, we are available in the college. Okay. Any other questions? So I'm ending this session. So with this, we complete the syllabus. So if further any queries, any questions, you can always contact us. we are available in the college. Just make it for 10-15 minutes or half an hour maximum. We'll clarify your doubts. Thank you.